Welcome to What to Expect When You're Connecting, a podcast for IoT professionals and the IoT curious who find themselves responsible for growing, executing, or educating others about the challenges with connecting products and services to the internet. You'll learn from industry experts who understand those challenges deeply and what they've done to overcome them. Now for your host, Ryan Carlson.
We're here talking about the what to expect when you're connecting in difficult, remote locations where bandwidth and hardware are working against you. We're here with Andrew Jarman of Toku Systems. He's a Chief Technology Officer. And we're also here with Kenta Yasukawa, the Chief Technology Officer and one of the co-founders of Soracom. Andrew, would you paint a visual picture about where you're deploying your products and hardware? And what does that look like? Set the stage for us.
Thank you, Ryan. In the oil and gas industry, there's lots and lots of places where you find instrumentation. You think mainly of your big oil and gas refineries, processing plants, and those areas are very well instrumented with traditional technologies because they're using wired sensors and they're running control systems, and everything has to work properly there or bad things happen. But in a lot of the upstream gathering systems, so from the oil wells and from the smaller pipelines to some of the remote facilities, there's not a lot of infrastructure in those locations, right? They're further away from the centers, and there's often not a lot of power out in some places. And so they're not frequently instrumented very well, right? There's a lot of drive up, check out that things aren't leaking, that pumps are running, and that's as far as people go in many cases. Now, over the years, of course, the higher producing assets are instrumented better because there's more money there. But there's a lot of applications where people didn't instrument it. So in recent years, as technology's gotten cheaper and some of these technologies like the cell connectivity and IoT types of sensors are more emergent, it now opens up the possibility to put things like pressure monitoring on places which historically haven't had them, right? So you go out there, but now you're not in the cities or close to cities. You're now in the middle of nowhere. So you've got locations where there is no power. If things are powered by gas sources to run equipment, so it has to be battery powered. It's cold, right? Especially in Canada and northern United States, it gets down to minus 40 at night. So the temperatures are extreme. There's not a lot of sunlight, so your typical solar panels, they have to work all the time, not just most of the time. So in the middle of winter, on Christmas, it's dark, lots of night, and it's cold. And so, the power systems struggle to work properly in those times. You get snowstorms for 2 or 3 weeks at a time, so very poor sunlight for your charging. And then, of course, there's the connectivity part. So you have to have connectivity to your cell towers if that's what you're relying on. Some places are in forests, some places are in valleys. So you end up with a mediocre at best signal in many of the locations. So all those provide challenges just to get anything to work properly. And then on top of that, you have to have hardware that can actually work in those environments. So oil and gas applications by their nature are hazardous, right? You've got explosive gases, you've got things that burn and blow up. So they really don't like you putting equipment that's not certified. So the equipment has to be certified, either Underwriters Lab in the States or CSA in Canada or equivalent bodies throughout the world. So the equipment is expensive to design and test and go through all those certifications. And then when you install it, it has to be installed according to the right criteria, right? So getting an IoT device that has a cell modem built in. The cell modems are relatively power hungry. To transmit RF energy, they need peak currents that are not for some of these small things that are intrinsically safe. It's easier, but when you have a power hungry device while it's transmitting, to do that without causing damage or to meet with the safety certifications, it's a lot of challenges to get a product built and certified to do that. So all those add a lot of cost and time to market to bring products to work. And then you have to write your software to work properly with all the edge cases that happen in these applications. And then there's no one there. You can't just drive up and go look at a log or look at a screen. There is no screen. There's no one there. So, you have to know what you're doing and work hard to anticipate all the problems that could show up.
I'm hearing these are devices that are in locations that are difficult to service. And even if you could service them, you're probably potting them in epoxy or you're putting them into enclosures that are challenging to get into. They require as much power efficiency as possible since you're not going to be pulling off of a line someplace. And when you do get signal, you're pushing peas through a straw, trying to maximize the throughput of whatever limited bandwidth you have access to.
Absolutely. Right. And then troubleshooting, right? When things go wrong, who can tell you what it's doing, right? You have a limited user interface, if anything. That creates a lot of challenges to supporting a large network. If you have hundreds or thousands of devices out there, you're proactive at how you look for data problems and react and work with your customers to get them back online.
There's multiple sides of this coin, and I don't even think it's two. So we're looking at another geometric shape of some kind. Mm-hmm. And there's the hardware, there's the embedded software, there's the actual software that you're communicating with out into the cloud, but then there's all of the cellular infrastructure for all of the packet routing and for the protocols. And so I'd like to actually turn this question to Kenta. Over the years, knowing that cellular is very power hungry, how has the evolution of cellular come to meet some of these specific needs? And where have you, as someone who lives in this space, had to find new ways to evolve cellular to address the gaps, maybe where traditional cellular has fallen short?
Yeah, definitely. The cellular network and the radio technologies, they evolved to support more bandwidth, more rich applications. But there are certainly needs for supporting those, low power consumption devices. And definitely when it comes to using regular cellular module for the use cases that Andrew and Toku Systems are working on, the oil and gas industry in general, those you don't require high bandwidth. You don't want to reduce the battery consumption and reduce the overhead for communication. So 3GPP has actually worked on to evolve cellular standard to support those low power communications. So probably our audience may have heard LTE Cat-M or NB-IoT. Those are evolution of cellular LTE technology to reduce the bandwidth, but reduce the power consumption as well, so that they can support the low power footprint devices. So it has a limited the bandwidth, but that actually allows the modem to be simpler, so that the modem cost can be also lower. And because it's simpler, it doesn't have to consume too much energy to communicate. And also it has some enhanced technology to put the modem into low power sleep mode. There are some technologies that LTE Cat-M supports, for example, EDRX, that actually allows modem to sleep for a longer period of time than the standard high bandwidth LTE modules. There's also a power saving mode that can actually put the modem into low power energy consumption mode and keeps the battery for a long time. So there are these technologies that can be applied to oil and gas technology industry, and also those devices in the remote. And also on top of that, that's the kind of underlying cellular technology world evolution towards the low power battery use cases. Another thing that we have been doing on top of that to reduce the communication overhead, if you have to do full-fledged secure protocols and all the TLS negotiations and everything on top of the cellular connections, it would cause a lot of data overhead, and also has to consume the processing power, and that actually ends up draining more battery. So when we launched our service, we have focused on supporting all these battery powered devices and IoT devices so that they can efficiently communicate with cloud backend. So we have come up with a solution to receive data over our cellular link. That link is provided from us and our partner carrier. So it's not going through the internet. This link can be used as a trusted communication between IoT devices and Soracom platform. So this part, you can use the low overhead protocol And without actually putting authentication information, we can authenticate and see who is sending data. So we can receive it securely. And then we can apply customer provided configuration and credentials and security mechanisms to forward the data to customers' cloud backend. By doing that, we can actually support to build end-to-end secure IoT architecture while having low overhead and low data consumption on the IoT side. By combining all these, we can optimize the data consumption and build an efficient system.
My understanding is that there's two different sides of the cellular game. There's from your device to the tower to the carrier, and then the carrier typically goes right to the public internet and then connects over to your servers, whether it's on AWS or Azure or wherever. And that all requires an encrypted signal with TLS, which is a bunch of packet headers. So it just adds extra strings of code and characters. And you're having a heavy lift that goes from the device to the tower to the data center. And what you're saying, Kenta, is you've shrunk the requirements between the device and the data center in the cloud, and you then add the packet headers, you add the encryption, and then communicate from the Soracom servers to the cloud server. So AWS, whoever you're talking to, gets all the encryption that they're looking for, the extra commands and authentication, and saving people like Andrew that heavy lift, right? Reducing the burden. Maybe Andrew, talk to me about your experience in having to deal with data overhead, paying for it, powering it, using battery life to move it across the airwaves. I'd love to hear your practical experience with that.
Yeah, that's a great point. And actually, that's one of the biggest selling points that I was very pleased when I found this on the Soracom website, is our initial product didn't have encryption, which of course we knew we had to get there, but we had to get something working. And then we needed to start looking at adding encryption on top of it. So we use MQTT, and so we had to be using something that the MQTT server could use, which meant we had to do a TLS wrapper around the socket connection. Well, our processor is only running at 16 megahertz, right? And sometimes we can slow down to 8 megahertz. And that's as fast as we run it on our controller. It's equivalent in horsepower to like an old PC from 1986, right? We were able to do everything with that. So doing a full TLS handshake, we even got the libraries, and we could do all that stuff on our client libraries, but it took so long to just do the elliptical curve calculations that the connection would drop, like the server would reject the connection. So we would either have to look at boost up our clock speed just to do the TLS handshake, or all sorts of stuff, right? And it was just very challenging to get that to work, as well as all the code added on to our microcontroller to implement the TLS libraries. And a lot of them aren't designed for deep embedded applications. So it was just a real challenge. So with using a product like Soracom has with their Beam and their virtual private gateways, we keep it encrypted by the nature of the cell technology with the APNs and so on. But we can just keep using our code as it was before. We just changed our endpoint to go through the Soracom proxy, and it did the TLS wrapper to our MQTT server. So in a few short days, we got that working, and it's like, that was it. Yeah, that's it. So it was great, right? I knocked off a pretty significant development effort in as much time as I was just trying to get the stuff going. And it was implemented and pushed out to our field devices in a few weeks. So that was very, very helpful. And then the power consumption there is better too, right? With embedded devices, clock speed means power, right? So if you can lower your clock speed, you lower the power consumption. And then all the TLS also adds a lot of round trips between the device and the server to get the handshake done. And that adds latency, and that is also measured in power, right? So everything comes back to power consumption. So the quicker you can get something done at the lower clock speed, it means you're saving power.
It's almost a trifecta. Reducing how much data you need to send reduces how much processing you need, which reduces how much power you need. And it also reduces the cost, right? If you're sending less data over cellular, you're paying for less data over cellular, right?
Absolutely, right? Yeah. So it cuts your cell costs and your latency. That's actually a bigger factor, is that the more your time you're spending sending messages back and forth, you're keeping the modem powered on longer.
So Kenta, what was the initial impetus? Where was the push to add a functionality like this into Soracom with that unified endpoint or a SSL proxy of some kind? Was it people trying to bring non-encrypted devices into modern cloud integration, or was it specifically trying to just reduce the actual power consumption or processing requirements?
Actually, you know what? We designed and developed this product for the specific needs that Andrew was talking about. So the TLS negotiation and all the cryptographic processing is hard for the low power devices, and it could be already a challenge for IoT devices to be used in reality. So back in 2015, when we launched our cellular connectivity API and management platform, that was definitely the foundation that we have focused on first. But at the same time, we also worked on this capability of offloading TLS and authentication workload from devices to cloud. So that was what we have been doing since the launch. And the reason why we started to look into that is I used to work as a researcher for connected home, connected car, sensor gateway, and all these, kind of early days IoT projects. And always I was wondering how we could actually run all these security protocols from the device to the cloud all the time. And another challenge that you might face is how to properly configure this authentication credentials to each and every device. That's already a headache if you have to build thousands or tens of thousands of devices and have to manage that in a factory. And then after that, you would have to rotate credentials over time. So by using our connectivity ID in cellular network, it's SIM card provides an ID and authentication. So it can be used as an authentication token. And then we can establish a secure link by using our private secure cellular network. So we can offload authentication and encryption to cloud side so that the devices can be more efficient and the data usage cost can be lower. And that was actually one thing that I'm so excited when you said, Andrew, is that actually offloaded your development time, which is an important resource in IoT development project. By using our capability, you didn't have to integrate TLS library into your device, and you could actually just change the endpoint to Soracom endpoint, and you could actually apply TLS integration by doing that. That was another thing we wanted to do. We wanted to offload developers' time to our platform services so that you could focus on the most fun part of IoT, that is to build applications and services. What you said actually made my day today.
It's great when technology works. There's actually another point with that kind of methodology, is that right now we have all our devices send data to one server instance. But if we ship the same product to, say, different parts of the world, or to, say, a large customer who wants to run their own MQTT server, if I don't use something like Beam, I would then have to go push out the endpoint down to the devices, maybe before they ship, which is another step in my logistics. With Soracom Beam, I can go just change the SIM card to belong to a different pool, and on the server, change the endpoint that it's going to. So it's actually added an operational savings in that kind of application, where if a customer wants to take over the MQTT side and run some other thing besides what we're doing, we can just make an endpoint for them and change it on the fly, and it's done in a few seconds. So it's a logistical improvement as well.
This reminds me of, in the marketing world, the ability to take one QR code and put it on the back of your business card. And that QR code actually links to a dynamic web space where you're actually on the fly changing how that QR code routes. So it's going to like a tiny URL, and then you get to actually change it up. So that could be your latest event or whatever you need it to be. And in this particular case, you're getting to ship the same device with the same profile, the same credentials, and it's the SIM that is the unique fingerprint. And then you just say and assign that SIM number to a group that might have a different set of rules. Is that right, Andrew?
Absolutely, that's great, right? We do that for testing, right? So we can send things to test servers. I just grab a device off the shelf, or do other demos or things that are a little unusual. It makes it very easy. So it's great. Love it.
Yeah, I'm so happy hearing that you can. Just for to explain to the audience, the Soracom Beam, our product to offload TLS encryption and authentication, you can actually define group of SIM cards or devices and apply different endpoint configurations. So devices can just send data to one single unified endpoint that we have. There is no change in the configuration in the device side needed. But you can define devices into different groups, and each group can have a destination server configured. So one group can be test group. The data can be forwarded to test MQTT server. One production group can send to the production server. If there's a group in a specific area that should use different server, you can just apply the configuration. And you can just change the group level configuration from one server to another. And all the devices, the data destination will be changed at once. So the IoT device management can be easy as well by doing that. I'm glad you have been using that feature.
Do you have a lot of oil and gas customers who are in the oil and gas space?
Yeah, we have a customer in Japan called Nichigas. They have deployed the network control units for legacy of the gas meters, and they have been sending data from time to time by using both Cellular Cat-M and also Sigfox. That's one of our largest customers in oil and gas.
Well, interesting.
Yeah, Andrew, are you doing certificate management at the device level on your hardware, or are you leveraging the SIM for management?
Yeah, we're not using certificates right now. During our manufacturing process, we push out a unique serial number and synchronize the passwords to be used with our MQTT server as well as on the device. But we are looking at using certificate authentication down the road, in which case then would use a certificate management that would be provided through Beam to add the certificate information, and we can use that instead.
Would that reduce by not having to have that that credential at the device level and just letting that unified endpoint handle that handshake? Does that reduce any additional processing power, or is it more on the manufacturing side?
More on the manufacturing side. And of course, when you have pre-shared secrets, you have to manage the security of the pre-shared secret. And there's other operational and data security things that we have to do. So, we keep all those, encrypted and stored away so that we can recover them. Of course, you can imagine having thousands of devices and we lose the secrets because we had to rebuild the MQTT server. That would just be horrific. You put a lot of things in place to make sure that can never happen. But certificate management through Soracom would be even better, because then the device doesn't even have to manage it at all, right? We control it.
I remember a contract manufacturer that I'd been working with at a past company, and we actually they actually sent someone with the aluminum sided spy suitcase, everything but the handcuffs, I guess, but actually went into the factory with the USB drive, and they had to observe the chain of custody on those secret codes that were going to be installed on the devices. They were there for, I think, 6 weeks in a hotel near the manufacturing facility to just oversee that those keys weren't ever, going in the wrong place, because it was a fairly sensitive application. So just having to manage, as you said, keep track of all of that stuff and to eliminate that seems like it would, for even some really sensitive applications, eliminate that need, since there is no duplicate SIMs out in the world. Right there.
Exactly. Yeah.
So, talk to me a little bit about the balance, the dance that you play between optimizing the hardware itself and the challenges that you've had to overcome at that level, and then firmware side, that handshake side with the MQTT and then the cloud server. You've had some unique situations, like how long your sessions can be open. Can you talk a little bit about that?
Yes, certainly. As I mentioned before, time that the modem's on is absolutely critical, right? When the modem's powered on, it's taking 50 to 100 times more power than the device takes when it's just sampling and recording the data. So we really want to minimize that. We sample and store the data to flash. So that is very useful to make sure that we don't lose any data if the cell side drops off or we have to retransmit or whatever. But once we get the data in memory, we then want to send it over the server over the link channels as compactly as possible. So we've worked hard to pack those bits in as tightly as possible. So when we send in our 1 second pressure data, and we typically send it in every hour, so we gather it all up and then we send it in an hourly burst. So we will take all that data and we strip out timestamps, we strip out extra bits. So we don't send floating point numbers. We strip it down to an integer, a scaled integer. So it's maybe a 100th of a PSI or a 1,000th of a PSI. Pack in all of that as tightly as possible into MQTT message. So we're basically bit packing it and sending it over the MQTT message. And then the server then, of course, reverses that and turns it back into some of the web guys like better JSON or all sorts of very wasteful representations of data, but more standard-based. The amount of flash, and I mean the RAM we have on these processors is only 128K of RAM, right? So you can't put large strings in there or anything like that, right? So you have to be very aware of how much you've got for memory and flash storage, and then as you pointed out, packing in the data to go over the wire cuts down the uptime for those messages. So when it's a race. As soon as we turn that modem power on, we've got to do everything we can to get connected as quickly as possible, send the data as quickly as possible, and then disconnect as quickly as possible, and then shut everything down with all the retries and error handling and stuff that you need to do to make sure that connection gets through.
What is that optimization process? What did that look like? Were there any big breakthrough moments or any ahas? We got it down to once every hour. We got it down to from once every 5 hours down to once every hour. Or is there anything along those lines where little changes make big results?
Probably less joyous or triumphant, because our firmware guys were old. We grew up in the Apple II and PC days. So the best firmware guys are people who wrote DOS programs, because it was an embedded system. Like, you didn't have all the abstractions you have today. If you wanted to write a serial port on a DOS machine, you had to write your own interrupt service routines. I mean, that's how horrible it was back then. So the people who grew up and wrote code back in those days are pretty good at writing embedded code for microcontrollers. So we knew we had to just dig back in the trunk of all the old programming techniques we used to use back in the day and apply it to the microcontrollers we have today. So a lot of those techniques. But, to put some numbers in perspective, in an entire month of sending 1 second resolution data, and this is high resolution pressure data, we would send less than 15 megabytes of cellular traffic. So that's hourly transmits with 1 second pressure readings. So every hour it's sending another 3,600 seconds of data in, and all that's less than 15 megabytes. That's not even a picture right on your phone. So yeah, we're very pleased about that.
Yeah, if you do it in JSON, it would explode, right?
Oh yeah. So yeah, you have to be very miserly and just really consider everything you're doing. Like, well, how often do we need to send that? And does that go every minute? Or can we put that every hour? And you have to, of course, your primary signal every second, but you have to just think carefully how much you want, how much resolution do you want, right? Rather than say the floating point, send it as an integer and just scale it, and then just be aware of how many bits is really important. There's no point sending temperatures to 7 digits for ambient temperature. No one cares, right? So all those little tricks, you have to be aware of just to try add some sanity to what's going on.
So by working with the binary data at the device level and then translating on the latter half, that's just right there is just, why even optimize when you just send less characters to begin with, right?
Right, exactly. And you'd think, oh, well, let's just compress it. Well, really, there's no point using the typical compression algorithm like your gzips or some of those other things, because if you have a small amount of data to send, If you can reduce what you're sending to begin with, that strips it down. But all those sorts of lossless data compression techniques have an overhead to them. And so when I was doing the analysis of this, the overhead wasn't even worth what we're sending. If you can just reduce the size down, if you're only sending 4 or 5 kilobytes at a time, the gzip algorithm takes more overhead just to get started, right? So just keep it all simpler, less code, less things to go wrong, and it's easier to debug it.
It's where the treatment is worse than the symptom itself, right? Like, this medicine is, what are the side effects? It doesn't sound like I'm actually going to feel any better by applying the compression to what you're doing. Kenta, you had a question.
Yeah, Andrew, do you have a way to change the frequency of sending data or the measuring the pressure value when the devices are already deployed in the field?
Oh, yes. Yeah, we can. So we do everything over MQTT. Just there's, I think, a quote that's the best part is no part, right? If you can get rid of extra things that you don't have to put on there, then why add more stuff, right? So we send commands out to the device using MQTT as well.
I see.
We can change the sample rate. We can change how often it calls in. If, of course, if the device finds as a fault or pressure goes out of alarm limits, it calls in right away, right? So if interesting things happen, it calls in without waiting the full hour. We can do firmware updates over MQTT. So I call it MQTT file transfer protocol. So it's MFTP. It's a very simple way for the device to go fetch a file, which is a new firmware download using MQTT messages. Because it's the tool you got. Might as well just use the tool. It's maybe not the most efficient transfer, but how often do you send firmware updates, right? So, if it's if you're doing deep embedded, just simplify. Less is more.
Mm-hmm.
If there was one thing that people took away for their low bandwidth, low power, constrained situation, what is the one thing that you could recommend that provides the greatest gains in power savings or whatever that might be? What's the one technical thing that they could be implementing that you'd recommend?
I think knowing what your hardware does and how does it work, you really have to start with that. Whether you're buying hardware from someone else or designing it yourself, know how it works and understand clock speeds and how to manage how the processor works, because that's really the key to everything. If you can manage your clock speeds, you can manage your power, and then from there, all good things happen. And then with that too, data storage sizes, costs, transmission costs go a long way to be able to keep your costs down ongoing and to keep your power consumption down.
Kenta?
Yeah, since Andrew has already talked about so many techniques that you can do on firmware, I will focus on the cellular communication part. When it comes to reducing power consumption, that the cellular or any kind of communication or wireless communication, make the modem sleep as long as possible. That's the key thing. As Andrew said, if you keep the modem open, that connection for a long time, that consumes a lot of battery. So reducing the time to send data is really important. So because of that, the protocol negotiation should be as simple as possible. Maybe if you can completely remove the protocol negotiation and you can simply send data, that might be the best. But in that case, you might lose the ability to do all the benefit of using like TCP or MQTT. So there's always trade-offs. So you need to think about the right protocol. But by reducing the modem open time or air time, that's the best thing to reduce the battery consumption. And also by reducing the protocol overhead, you can pay less for cellular provider, which is also important. It may sound weird for me to say that, but we are actually here to make your IoT projects successful. So we really help to reduce the data consumption so that we can have a scalable, robust structure that is also reasonably priced when it comes to doing more with less.
When it comes to multi-carrier support, having to choose between a single provider or where Soracom is looking at multiple carriers, how is that impacting the work that you're doing with Toku and the device functionality out in the field?
Oh, that's really good you brought that up. In the past, both before we discovered Soracom and when I worked at another company that we were also doing IoT types of products, managing cell companies was a bit of a pain, to be honest. Either you're using a primary carrier, so say in Western Canada, we might use TELUS. They're the old government telephone people, so they were very strong in Alberta. But you get outside of those areas, or you get to an area where maybe TELUS doesn't have a tower, or it's not the best carrier, then you want that option to go with a different carrier, or you get a trial customer or a new opportunity in a different part of the country or in a different country, and then you have to scramble to get your cellular communications all set up. So these global roaming SIM cards like Soracom has, or these agreements with all these carriers, it's fantastic because I can use a single SIM card and ship it inside the device, and we can just figure it out once it gets there. So if there's a ridge or a obstruction between our device and a particular carrier, we've got other carriers to fall back on, and it just works, right? And that's the beauty of it. And then over time, figured, okay, this is actually working pretty well. Let's start pulling all the SIM cards out of our existing products. So Bell Canada kind of lost out, and every device that touched our operations got the SIM card ripped out of it, and a Soracom SIM card went in, and that's that. So it just saves so much hassle, right?
In 20 years of doing IoT devices, changing carriers means having to go out and switch the SIM, right? So Kenta, how is it that Andrew and his team are able to take advantage of an entirely new plan, but not having to swap out the SIM card that's probably buried deep within an enclosed, hard to get at piece of equipment? Could you describe that process?
Yes. Yeah. At the early stage of platform development, we were aware of that. It's nearly impossible to replace the existing SIM card or eSIM in the devices that are already deployed in the field. And we knew that our subscription plan that we had at the beginning would be the best for forever. So we had to think about the way to remotely update and over the air and push down new profile whenever we have a new subscription plan that is beneficial for our customers. So that we were aware of the challenge since when we were working on our own SIM product. We have our global connectivity SIMs that we design and work with our SIM vendor to. And so we have all the software that we can install in our SIM chip and ship to our customers. And when we launched our first SIM product, we didn't have the backend infrastructure to update the profiles over the air, but we added that capability within our SIM card from the day one, so that we can eventually use the feature to push down new profile. So we launched that feature later on, and how it works is that you can select a SIM or a bunch of SIMs and select push down new profile whenever it's ready. And that will trigger our over-the-air update framework for SIMs to send a message and download the profile onto existing SIMs. So in this case, we are now launching a new Plan US Max that allows access to all the three major carriers. And you can select the SIM and push down new profile. And that happens automatically and behind the scene. And the SIM will be able to switch to the new subscription plan once it's received, and the modem can talk to a new carrier by using it. That's how it works. We call it subscription container because the subscription plan is contained in a container and delivered to already deployed SIMs in the field.
Man, this reminds me a whole lot of like the Kubernetes and other sorts of containerized deployments. What I find interesting though is like when I've got my iPhone and I wanted to switch carriers, it was using EUICC, and I had to go in and as the end user had to go and authorize a bunch of things as a consumer. But this isn't the same technology that a commercial handset is using. You developed something that can be deployed from a fleet manager. So like an Andrew or someone who has access to that list of all the deployed SIMs can make all of those changes without needing to do any sort of end configuration or end authorization.
Yes, actually, we support both the EUICC, what you use on iPhone, Android devices as well. So we have a customer and our own application to download Soracom profile onto phones and use it. So that actually requires the user's operation on the device. But that's certainly useful for some use cases. We have supported that. We also, that's called the EUICC Consumer Profile Management. And we also support EUICC M2M profile management. That one, you can push down new profile to existing EUICC systems by using standard GSMA technology. That's also supported. But we rather developed our own solution as well, in addition to these standard technologies, because when it comes to adding and downloading subscription plans that we manage, we don't necessarily have to have the entire EUICC framework to deliver the profile, because we manage and we can make sure we can use our over-the-air update keys. We could implement much lighter way of doing subscription management compared to EUICC profile management. That's downloading entire virtual machine onto server rack. We support that, but it's heavier and requires much more communication overhead. Instead, our subscription container approach is like, as you said, Ryan, it's like Kubernetes. We actually have a lightweight container of subscription plan and push down it to existing SIEMs over the air. So we have supported both, because by doing that, we can apply our new subscriptions to a wide range of SIEMs and devices.
I'm asking this because I don't know the answer, but for someone like Andrew, who was talking about even getting the subscription container updated to get Plan US Max added, would EUICC being a heavier lift with a larger framework, would that be a harder thing to deploy in these remote low bandwidth locations?
From my side, my biggest concern when looking at the subscription containers is how long the modem had to be on and how long did I have to leave it on for this magic to happen. I don't know what all goes on the SIM card. I know there's a lot on there. It's not just a memory card. And so the bigger the download that the SIM card needs means in a poor cell phone connectivity area, how long would that take? How long do I need to leave the modem on? Because there's no feedback to me that all this magic is going on. So far, the devices I've tried have just worked. I added some commands to the new firmware to tell it, next time you call in, stay around. Don't hang up so quickly. You just have a chat. And so I can synchronize that with enabling the container to try minimize that. Like you can imagine someone had to helicopter into a location to go install one of our devices. If that thing goes off net, it's a big deal, right? So I'm really reluctant to do anything that would mess that up. And we're very careful how we do the dance with the network, especially. That whole dance has to work properly.
Gentlemen, I'm going to leave us there. There's still so much more ground to cover. Until then, thank you for your time.
Thank you, Ryan.
Thank you. It was fun.
This has been another episode of What to Expect When You're Connecting. Until next time. Final question for you, Andrew. What is Soracom to you?
Oh, wow. To me, Soracom is a very valuable piece of our infrastructure to enable the device to our cloud connectivity. Like it's become bigger and bigger, and as I've explained to other people in our company, having one provider, the one SIM card provider, I have one part number that has a Soracom SIM card in it, and then it just works, right? If it works wherever I need to ship product to, it simplifies my supply chain. It simplifies how I manage devices, and it provides me a valuable partnership to get my data to my server. So that's everything, right? Without that, I don't have